Welcome to the Explainer. Have you ever wondered why, when you turn a volume knob, it doesn't always give you a perfectly even increase in sound? Or why a motor speeds up and then just hits a limit? Well, today we are diving deep into the world of nonlinear systems. And you'll see how a really clever mix of simple building blocks can help us make sense of even the most complex, real-world behaviors.
So, this is really the heart of the problem we're tackling today. You know, we often start out learning about systems with these nice, clean, straight line equations. But let's be honest, the real world is, well, it's messy. So, what happens when the actual parts of a system, the sensors, the motors, the valves, don't behave in that perfect, predictable way? How on earth do we capture that reality in a mathematical model?
All right, here's our game plan. We're going to start with the basics of system modeling. Then we'll look at the go-to method, the linear approach, and see just how powerful it is, but also where it kind of falls short. And right when we hit that wall, I'll introduce you to two really elegant solutions, the Hammerstein and Wiener models. And then we'll wrap up by seeing where they're used out in the real world. Let's jump in. Okay, let's get into it. Imagine trying to figure out how your thermostat works. You turn the dial, that's your input, and then you watch how the temperature changes over time, that's your output. System identification is really just that process, taking data and building a mathematical model that connects the dots between the two. And the whole point? To be able to predict how your house is going to heat up or cool down later on.
So, the most common tool in the toolbox, and definitely our starting point, is the linear model. It's powerful, it's pretty easy to work with, and honestly, for a huge number of systems, it works unbelievably well. There's a really good reason it's the bedrock of system modeling.
Now, I know this equation might look a little intense at first glance, but the idea behind it is actually super simple. All it's really saying is that the output of a system right now can be predicted by just looking at a weighted mix of past inputs and outputs. Think of it like a recipe. The phi part is your list of ingredients, all that past data, and the theta is the recipe card, telling you exactly how much of each ingredient to mix in to get your final dish.
To make this less abstract, let's go beyond a simple thermostat and look at a really practical example from the source material, a solar heated house. The challenge here is to model how the temperature of a heat storage unit changes, and it's based on things we can control, like a fan, and things we can't, like how sunny it is. So what's so cool about this is how we can take a complex, real-world thing, like this house, and translate it into the language our model understands. The fan speed, that's our input. The temperature of the storage unit, that's our output. And the sunlight, that's a disturbance that we can actually measure and factor into our equation. It's this kind of structured thinking that lets us use that powerful linear model we just talked about. But, and it's a big but, here's where things get tricky. That nice, neat, straight line assumption, it often breaks down. The real world just isn't always linear. So what happens when our simple model runs smack into the messy limits of reality? Right, so here's the crucial point. Physical things have limits. A valve can only open so much. A motor can only spin so fast. An amplifier hits a max volume, and that's it. This behavior, where the output just flat lines even if the input keeps going up, is called saturation. And it is, by its very nature, non-linear. Our straight line model just can't handle it on its own. So how do we deal with this? I mean, we could just throw away our linear models, but that seems like a waste, since they work so well for the dynamic part of the system. Instead, let's check out a much more clever solution, a little twist that lets us keep the best of both worlds. First up is the Hammerstein model. This model is absolutely brilliant for situations where the nonlinearity, the weirdness, happens right at the beginning. A perfect example is a guitar pedal. You stomp on a distortion pedal, that's a totally nonlinear effect, and then that distorted signal goes into the pretty linear amplifier. So the input signal first gets crunched by a nonlinear block, and then that new transformed signal gets fed into our good old linear model. And the Wiener model? Well, it's just the mirror image. It's the perfect tool for when the nonlinearity happens at the very end of the process. A classic example is a sensor. The actual physics of the system could be perfectly linear, but the sensor measuring the output might not have a perfectly straight line response. So the Wiener model handles this by letting the output of the linear system pass through one final nonlinear block that represents that sensor's quirky behavior. And this really illustrates the key difference perfectly. It all boils down to one simple question. Where in the process is the nonlinearity? Is it in the actuator, affecting the input? You're going to use a Hammerstein model. Is it in the sensor, messing with the output?
Well, then you want a Wiener model. It's just a really elegant block diagram way to think about these complex systems. So, this isn't just some neat trick for academics. These models are absolutely essential for accurately describing a huge range of systems out there in the real world. So, where do we actually see them making a difference? Oh, the applications are all over the place, and they're super interesting. We see them in robotics, helping to model motors that hit their torque limits. In chemical engineering, they're used to describe reactions where the rates aren't constant. They even show up in biology and medicine, believe it or not, helping to model things like how your pupils respond to a bright light. Basically, anytime you have a system that's mostly linear in its core dynamics, but is constrained by physical hardware, these models are going to be your best friend.
So if there's one big idea to take away from all this, it's that we don't have to start from scratch. We can stick with our powerful, well-understood linear models and just bolt on a nonlinear block at the beginning or the end. This gives us the best of both worlds, a model that's powerful enough to capture the complex dynamics, but also realistic enough to respect the physical limits of the real world. And that leaves us with a really fascinating question to chew on. We've just found this elegant way to handle nonlinearities at the edges of a system, but what about systems that are nonlinear from top to bottom? Or systems where the rules themselves seem to change over time? Well, that's the next frontier, isn't it? Pushing forward to build even more accurate and insightful models of the amazing world all around us.